All right. Hey guys, I'm Stan Krementsov, originally from Russia. I've been living here in Vancouver for about 12 years. The last couple of years, I've been working as a senior machine learning engineer for a startup called BioConscious until about 2 weeks ago. Now I'm looking for jobs. So if you have any interesting positions in machine learning, uh, feel free to let me know either on Slack or on Meetup or wherever. Alexis seems frozen. I guess everybody else can hear me, right? Yeah.
Sorry, I'm just eating.
Okay, yeah. So basically, I like reading about. I mean, first of all, one thing that I like is reading papers about machine learning and deep learning. And one of the projects that I started this year is dl.reviews, which is a site where I review deep learning papers once every few weeks, the recent ones that are of most interest to me. So you're welcome to check that out as well. And my interest in Kaggle competitions, when I look at them, my idea is to try to learn as much as possible about the different methods that people use when they, like the winners particularly. So for this presentation, what I would like to do is not so much go over like the small details of like how to deal specifically with like audio and stuff like that, but in general, go over the theoretical methods that were used and provide some perspective on that. And I understand that we have a group of people here, some people who might be quite familiar with machine learning, but also a group of people who might be just trying to get into data science and machine learning, and they might not be as familiar. So I'm not gonna get into any really like complicated math or anything like that. I'll try to keep it simple, but hopefully it will still be interesting to those people who are more familiar with these topics. So let's see. Am I supposed to share my screen now, or?
Yes, you should share your screen with the slides.
So basically, it gives me a PowerPoint slideshow. Is this working?
Yep, that's working.
So everyone can see my screen.
Mm-hmm.
Yeah, so like when I talked to Alexei and he said that this meetup needs a speaker for this Thursday, I said, yeah, sure, I can do it. But then I thought, like, which competition do I want to do? And there was the Google Landmark competition that recently ended, and this one. And this one seemed more interesting since it's like more unusual audio data. And also, I spent one semester at Cornell studying machine learning, so that's also during Hurricane Katrina because I couldn't study in New Orleans. So, okay, so let's see, how do I switch slides here? So the competition was 1,390 teams and $25,000 in prize money. So it was a pretty decent competition, and like lots of people competing. How do I change slides? What do I press?
Page down, spacebar, left click on the mouse. This is PowerPoint?
Oh, I guess, yeah, I guess I just need to switch to it because it wasn't the active application.
That worked.
Okay, so like at first, I want to go through the competition rules and review the training and test data that was provided to the participants. Okay, so this was a code competition as opposed to the competitions where all of the data is provided in advance and you're supposed to train a model on the training data and then apply it to the test data and just submit the answers. Here you had to actually create a kernel in the notebooks, and then like once you created that kernel, then the test data would be given to that kernel, and it's supposed to generate a submission of the answers. And the conditions, like 9 hours or less for CPU notebooks, 2 hours or less for GPU notebooks, no TPUs, no internet access. But it was actually possible to use external data as long as you put it into your kernel in advance, including pre-trained models. So I would say in general, it's pretty standard. It looks pretty standard for code competitions. So
sorry, Stan, could you train your own model and then put that into your as a starting point? You said pre-trained models.
It says this includes pre-trained models, so I guess it doesn't matter who pre-trains it. And actually, later on, when I get to the description of those models, I'm not 100% sure about what they were pre-trained on, based on the discussions that I saw for this competition. I'm not 100% sure if some of those models that the winners used, if they were just standard pre-trained on ImageNet or the sound data set that I'll be talking about, or the winners actually had to retrain them.
I wonder if you're allowed to use your own pre-trained model, but you have to make it available to everybody else?
I don't think so.
No?
Theory says you could pre-train on the competition training data.
Yeah, on the competition, maybe. Yeah,
so
I don't know.
The execution time is just to generate predictions for the test data. It's not to train your model as well. Well,
I mean, I guess you could do whatever you wanted with it. But yeah, I think probably, I didn't investigate that, but I think probably people already pre-trained models in advance.
I think 2 hours is really short if you want to train a model and run inference as well. I think if they wanted you to train the model in 2 hours, that would be really pushing it a lot.
Well, if you're just fine-tuning it, it might be okay, but yeah, I mean, my guess is that they probably pre-trained them in advance on their own computers or whatever kernels they had available. Yeah, so the trained data was 21,000 something MP3 bird call recordings from 264 different species of birds, I should say. I don't know if there probably were more actual physical birds there. One thing about it, those were somewhat long recordings, some of them, but the labels were just that there is a bird somewhere in that recording. The labels didn't specify where exactly the bird was. So in that way, the labels were weak because there was no time information, there was no information as to which part of the recording actually corresponds to that bird. So that made it difficult for many participants, and they mentioned it in their comments there. And here is an example of the data frame that was provided with this competition.
So all these recordings are in the wild, and so there's all background, other confounding noises that come with it?
Yeah, that was another problem that a lot of people mentioned, was that it wasn't just clear recordings of birds. It was birds, and there could have been some other birds there, and there could have been some background noises. I mean, usually I don't think there were too many other birds in those training recordings, but you never know. And in this data frame, there is a bunch of other information, but I don't think it was particularly useful. I mean, you can click on the link at the bottom of this slide where there is a nice notebook describing all of the distributions by all of those parameters. But I haven't actually seen people using those parameters in their models. I think pretty much everybody among the winners, they just used the actual audio data. I don't think which makes me assume that it probably wasn't that useful, to know whether the recording was made in the summer or in the winter and what year and who made the recording and stuff like that. So it was most of the winners, they just concentrated on the actual audio data on those MP3 files. And one of the big problems with this competition was that the test data was quite different from the training data in the way that the recordings were longer, and they each about 10 minutes long. I'm not sure if there were really 150 because I looked at some submission files and they didn't really contain that many rows. So I don't know, like in the conditions of the competition, it said 150, but maybe there were fewer of them. But those recordings, they had some noise and they had multiple birds within each recording. And the idea was to, like, for each recording, there were 3 tasks. 2 tasks were to identify birds during specific 5-second time intervals. And the 3rd task was to identify all of the birds in the whole recording. I guess here are the conditions. And there was an option of no call. So like if especially within like those 5-second recordings, if there was no bird at all, then you were supposed to say that there is no bird there.
So there could be different species of birds in a single recording.
Yes, there could be different species of birds.
Okay.
Yes. Yeah. And the evaluation metric for this competition was row-wise micro-average F1 score, which is like a whole bunch of words if you haven't seen that before. I mean, first of all, the F1 score, for those who don't know, is just the harmonic average of precision and recall. So you have your, like, if you just have one class of bird and you want to know whether it's in there or it's not there, then you, let's say you predict it's there and it's actually there, that's your true positive. If you predict it's there and it's actually not there, then it's a false positive. If it's there and you predict that it's not there, then it's a false negative, and so on. So you calculate those precision, which is the number of birds among those whom you predicted, that you predicted in that interval, that are actually in that interval. So basically how accurate your positive predictions are. And you have recall, which is the opposite, which is like if you take all birds that actually are in that segment, what percentage of them have you predicted that are there? And you always want to kind of optimize between those two, because like you can easily get 100% recall if you just predict every bird in every segment. But obviously it will be a useless model and it will have very low precision because most of the birds will actually not be there. Or you can have very high precision if you only look at the instances where you're like really, really sure that the bird is there, but then you'll have very low recall. So the idea of the F1 score is to find a good balance between those two. And this harmonic average is how it's calculated. But the question is, what do you do for multi-class prediction if you have multiple types of birds? And apparently there are 3 different ways of calculating, or maybe even more than 3, but these are the most popular ones of calculating, like averaging those F1 scores over different classes. So macro average F1 score, you can calculate the mean you can calculate F1 for each class, and then you can take the average over all classes. You can have a weighted average F1 score where it's the same thing, but you weigh it by the number of actual birds there in each class. So the classes that have more birds are more important in this case, or whatever problem you're solving if it's not birds. But in this competition, it was actually a micro-averaged F1 score, which means that you first combine all classes. So basically, you just count true positive, false positives, and false negatives for all classes together, and you don't really care which class it is. And then you just calculate the F1 score based on those precision and recall that you get from those true positive, false positives, and false negatives.
How balanced was the data? Do you know?
In what way?
Across bird classes.
Well, there is like statistics for train data. So basically the maximum was like 100, but there were some birds that only happened like 9 times there. But as far as test data, I don't know, because it was not provided. So I'm not even sure if the participants of the competition actually know how balanced it was. Because I guess their kernel ran, and I don't know, like I didn't see anyone actually providing this data. But it was probably at least somewhat reasonably balanced if you just go by the training data, because there were a lot of birds that had 100 recordings there, and there were probably some rare birds that had fewer than that. Okay, so what do we do with those bird calls? Like, how do you apply machine learning to that? On the left here on this slide, you see the time domain representation, which is basically just like the amplitude or whatever it's called of the signal. I'm not really an audio person, but basically you have the strength of the signal plotted against time. And that's not really how you can easily recognize a bird by the value of the strength of the signal at any given moment. What is much more easier to use is the frequency, because it's kind of like, how do you recognize a man from a woman? Because a man has a really low voice and the woman has a really high voice. I mean, I'm not a woman, so maybe I didn't do it really well, but yeah, so basically you want to look at the frequency, which is a much better indicator. So for the frequency, you take the Fourier transform, which is on your right, and you can take it for each small window. I'm not sure if this particular plot there actually had a bird in it, because I just took, this is an actual, I plotted this from an actual recording there of some bird, and I just took some time interval and I plotted this. So if you plot the frequency distribution for all times, not just one little time window, you get a spectrogram like that. But you can just plot it in regular frequencies, but you can also plot it on the MEL scale, which is usually used in this kind of applications. The idea is to create a number of buckets that are approximately even in terms of the change to the human ear. So when you go to higher frequencies, you'll have wider buckets, because the difference between 500 and 1000 hertz, as I'm saying here, is approximately similar to the human ear to the difference between 5000 and 10,000 hertz, even though the actual interval, the frequency interval, is 10 times larger there. And the way you create those MEL spectrogram, it's logarithmic, because the y-axis, the frequency axis here, is logarithmic. And the way you generate them is by using the LibRosa package, which is the standard package for dealing with all audio data, at least as far as Kaggle competitions are concerned. And actually, there is a version called Torch LibRosa, which apparently for this competition worked better than the average, the regular LibRosa version. And it was created by the same people who created the main model, who wrote a paper about the main model that was used by most winners in this competition, which I'll be talking about.
I think maybe a long time ago, we had a competition that was related to birds. And, of course, MEL spectrograms came up and the human ear came up. And I said this before, and here it is 2-3 years later, and I'm saying it again. Yes, but how does the bird ear work? Because the birds aren't singing so that humans can recognize them, right?
Yeah, but maybe humans evolved to be able to recognize natural sounds like birds. So,
well, but in general, the bird ear probably works very similar to the human ear. You're basically recognize, the birds recognize different frequencies, and because humans obviously can recognize frequencies, especially if you're into music, for example, you can hear different frequencies of sounds. And yeah, I would say birds are probably the same thing. So they don't calculate the log MEL spectrogram, but
But if there was a bird LibRosa package specific for birds, then you would probably use that in this case.
I guess, yeah, but that would be really specific. Yeah.
Sorry, thank you.
Yeah, so basically once you have that spectrogram, then you can just use the tools that you already have. You don't have to, it's an image. So why don't you just take some visual model that is pre-trained on like ImageNet or something like that, and just try to make predictions. And it turns out that it worked pretty well. I mean, maybe not the models that are just pre-trained on ImageNet and just directly applied to it, like, but maybe the models that are pre-trained on a specialized audio data set that I'll be talking about a little bit later. But essentially, it's the same kind of convolutional networks that are used for visual information. It turns out that they work surprisingly well for this task as well. And I'm like, for those people who are somewhat new to data science, I'm showing here like the basic structure of the convolutional neural network. So the idea is that if you just have a neural network that is like fully connected, each neuron and each layer connects to each neuron in the following layer, and treating this image as just a bag of pixels, then you'll have like a lot of extra connections that are not particularly useful, and you have like very high number of parameters in your model. So if you want to get a better, I mean, like if you just had a fully connected network, you would not be able to have like 100 layers in there because it would be an insane number of parameters. So basically, convolutional neural networks, what they do, they capture the specific positional information. Like you have like a small square, like 5 by 5 or 3 by 3, that produces the connection to each neuron in the next layer. And you have multiple channels, multiple convolutional filters that just look for patterns in this small square, like 5 by 5 or 3 by 3. And then you have a pooling layer that shrinks the image, and then you have another convolution, let's say if it's also 5 by 5 and in this picture, but because of the pooling layer, it's actually 10 by 10 as related to the original image because it has been shrunk. So this way you can find bigger features in the same layer. So it turns out like the convolutional neural networks, they basically started being actively used about like 8 years ago or something like that, the AlexNet. And like since then, no one really uses anything else for images. And then around 2016, people started using residual networks. So a residual network, or ResNet, and it has different variations like ResNext or ResNest or whatever. They are convolutional networks, but they're pretty deep convolutional networks, and they consist of multiple blocks that are all exactly the same. Or, I mean, sometimes there might be some variation, but the idea is you have this one block, and you just kind of build it up, like connect one to the next, to the next, to the next. And it's very easy to build a deep neural network using that. But the problem is when you're building a really deep neural network, if you just have those convolutional blocks, it will be pretty hard to propagate the gradient from the end back to the beginning through all of those layers. So what they do, they use those residual connections here. By the way, guys, can you see my mouse cursor?
Yes.
Yeah, so they have this residual connection that goes around each block and basically adds the input of each block to its output, which means that they have to have the same size. But then if you just had convolutional layers in there, then you would have another problem. You would have the signal that grows exponentially with the number of those blocks that you have there, because like if you have one block, you have a signal that like one here, and then you have another one here. So the strength of the signal after the first block will be 2. And then it will be the input to the second block, and then it will be 2 plus 2. It will be 4, and then it will be 8, 16, 32, and so on. And it will be a very unstable network and hard to train because you have those ReLU activations, which is rectified linear unit. So for positive values, it basically preserves the value. It doesn't saturate, which is a good quality why it's used, because when it saturates, it's much harder to propagate the gradient. But the thing is, if you didn't have those batch normalization layers there, it would be pretty hard to train them. That's why you have the batch normalization layers in residual networks. One of the reasons why you have them. Because like once you have a batch normalization, let's say for the second block, if the input is 2, the residual connection will give you 2, but the batch normalization layer in the block will normalize it to 1. So for the next block after that, you'll have an input of roughly 2 plus 1, 3, and so on. So it will not exponentially increase, it will just increase linearly. But what this means is that the biggest part of the signal actually doesn't go through the blocks. It goes through those residual connections, which means that the effective depth of the network is actually much lower than the number of layers. So like you might have like 100 layers, but the effective depth of the network might only be like 10 or 15 or something like that. But then the question becomes like what's the use of all of those 100 layers? If the effective depth is only 10 or 15, can't you just have 10 or 15 layers there? And if you have a neural network that just has 10 layers, you might not even need residual connections. But the beauty of this thing is that when you have 100 layers, if you read the lottery hypothesis paper, I don't remember the exact title of it, but I have the links to 2 papers that I actually reviewed on my site. First is about the shallow paths for residual networks. And the second one is about the lottery hypothesis. The idea is that it's pretty random, and the more of those layers you have, the higher is the chance that there will be some combination of weights there that will produce a good model. So there are all different combinations of those layers that were initialized with like random or somewhat random weights. So when you have a deeper network, even though the actual effective depth of the network doesn't grow that much, you get greater variety of combinations that you can have there, and that results in higher accuracy when you're actually making the prediction. So that's kind of the cool thing about residual networks. I don't know if you guys understand what I told about those networks. If anyone has any questions, you're welcome to ask. But basically, residual connections are used in a lot of like modern, basically in all top image recognition networks. There are usually some kind of residual connections. For example, like another one that people use is the DenseNet, which is similar to ResNet. But instead of just having residual connections over like each block, what they have, they just connect everything everywhere. And it adds a little bit of complexity, but it actually works pretty well as well. So it's somewhat similar to ResNet. And then the problem with like standard residual blocks is that they're pretty inefficient in the way that they have those bottlenecks layers with fewer channels, like with fewer filters inside each residual blocks. And you have those wider layers that are actually getting connected. So to make it more efficient, you can have an inverted residual block as they had in MobileNet v2, where you actually, the layers that are getting connected through the residual connection are the bottleneck layers with fewer channels. And that really reduces the number of parameters in the network and makes them easier to train. And also they use, to facilitate calculation, they also use depth-wise separable convolutions, which are, I'm not going to explain what they are right now, but you can follow the link if you are interested. And those inverted residual blocks, they were used in the efficient net, which was created by Google last year. And they used the neural architecture search, basically tried a bunch of different parameters for the architecture based on some sort of algorithm, how they choose them. And so which one produces the best efficiency and the best performance. And they use those residual blocks right here and depth-wise separable convolutions as well to really optimize it for efficiency. And like it is actually the efficient net. It is actually quite efficient. And I'm not sure if I put that. Yeah, I put that slide in there with the actual top one accuracy depending on the number of parameters. I mean, I don't think it's current. I think the slide was created when the paper came out in 2019. So now I'm sure there are better competitors to efficient net. But you can see that with the, like, it has fewer parameters, even like the B7, the one that has the most parameters, the efficient net, it actually only has something like 65 or 70 million parameters, where some of those networks have more and they don't have the same kind of image net accuracy. So basically, that was all about those like standard computer vision models. So how do we apply those to the audio domain? I mean, in the audio domain, there is like its own list of different tasks that you can do. You can do audio tagging, just basically assign a tag to each audio. Like, let's say, like if you just have one bird in each audio, you can say that this audio is this bird. Or acoustic scene classification, music classification, speech emotion classification. And one that is relevant to this competition is the sound event detection, where you don't just assign one tag to the audio, where you actually go through the audio and you are trying to determine, okay, between this time and that time, this happened. So let's say this kind of a bird you can hear this kind of a bird in this time interval. So the paper that is most relevant to this competition that pretty much all of the winners used, like the result of this paper, is this paper, Pre-trained Neural Networks for Audio Tasks, by Ki-Kang Kong from University of Surrey and ByteDance AI. And they have released their code and their pre-trained models in their GitHub repositories, so anyone can use those. So they have this audio set data set, which was not created by them, which was created by Google, which is a collection of like 2 million human labeled 10-second sound clips from YouTube videos with 632 classes. I mean, obviously, those are not bird related in any way. I mean, there might be some bird sounds there, I don't know. But it's like a general data set for training on audio, kind of similar to ImageNet in computer vision tasks. And they pre-trained a bunch of models, but they pre-trained them specifically for sound event detection, which is where you predict, as I said, like the start time, end time, and the type of event for each interval in your file.
Seems likely that in that set they would have some birds, the audio set. Even if you had a thing to detect birds versus not bird sounds, that would be a good starting point.
Yeah, they might have something there, like I would imagine, that has just some general bird sounds, but I would be very surprised if they actually differentiated between different types of birds.
Yeah, no, I wouldn't expect that, but you'd use that as a first step and then do your classification.
I mean, maybe there could be like 2 or 3 different types of birds there.
Mm-hmm.
Yeah, so basically there was this person from Japan, Hidehisa Rai, or however it's pronounced, who created a public notebook based on this paper and on this framework, which was pretty much used by all of the winners. I don't know if this person maybe would have scored higher if they didn't share all of this knowledge. But I guess like when people share like that, it makes the competition more interesting in the way that it's not just one person who has this knowledge. But
well, there's also, they do give prizes for most popular kernels as well. So hopefully you want something there.
I'm not sure if this kernel was the most popular. I think it was actually the second most popular. I think there was one exploratory notebook there that was more popular than that. But yeah, well, I mean, sixth place is also pretty good, I would say. I mean, like, I'm not sure if he won money, but like for Kaggle points, I think sixth place is pretty substantial. Okay, so basically you can have either a model that is trained on ImageNet, or you can have this specifically model that is trained on this audio data. But just like if you want to win a Kaggle competition, obviously just having a good model is not enough. You have to do a lot of other things. And one of those things is data augmentation. So because, I mean, especially in this case, because the data set is pretty limited, it's not huge, obviously. So the winners had to do all kinds of augmentations. Like, let's say with visual data, the way you do augmentations, you can do like rotations, flips, dilations, and it actually makes a lot of sense, because let's say if you have an image of a cat, if you rotate it, it will still look like a cat, or if you flip it, if you dilate it or contract it, then it will still look like a cat. Or if you add some noise, it will be a noisy picture of a cat. So it makes sense to use all of those augmentations that are pretty cheap and that give you all of that additional training data that you can train on. You can also generate synthetic data using generative adversarial networks, which kind of seems stupid at first glance, but it turns out, like, basically you have a generator and a discriminator, and the generator just keeps generating images, and the discriminator tries to determine whether it's the right image, like whether it's an actual image or a generated image. And you train both of those in combination. That's what the generative adversarial network is. And that synthetic data can actually be used for training. I mean, like, I read the newsletter by Andrew Ng, where he was talking about that, and he said that, like, those synthetic images, they're about 5 times less useful than actual images, but they're like hundreds or thousands of times cheaper to generate than to actually get and label actual images. So it's a good trade-off. But obviously it only works if new data stays within the same distribution and corresponds to the same label, because if you do something really random with, like, let's say if you have an image and if you just randomly mix all of the pixels in it, then it won't, like, if it was an image of a cat, it's not going to look like a cat anymore. So something like that would look a lot less would be a lot less useful. And one thing about, like, data augmentation, one way to do it is that has become pretty popular, and that was used by at least most of the winners, is Mixup, which is a pretty simple way. You basically, instead of just doing something to just one input, you take 2 different inputs and just take a linear combination of those 2 inputs and take a linear combination of 1-hot encodings of the outputs for those. So this turns out to be pretty good because it encourages your trained model to behave linearly between training examples. And when you have an image like that is like, let's say 70% dog and 30% cat, then this is taken from a FastAI forum. I mean, it might not look like anything to a human, but apparently images like that are pretty good for training those visual networks. But it's important when you train to pick mostly, like, they use this beta distribution to pick lambda values that are actually mostly close to either one or the other and not so much in the middle, because otherwise, like, it's important that most of the images that you train on are actually much closer to one of the images than somewhere like 50-50.
This is one way that audio is different from images, because if you take this 70% dog, 30% cat, you end up with something that just looks like not any kind of image. But if you take 70% one kind of bird, 30% of a different kind of bird, and add those up, I mean, audio does add linearly, and you'll get a sound that just sounds like a couple of birds at the same time. So mix up, I think, makes a lot of sense in that case.
I guess, yeah. And like, as I said, most winners or all winners, I'm not sure they use this. And as usual in Kaggle competitions, like all of the winners used a lot of ensembling. And ensembling is I guess I mixed those two slides up in the order. So it's a very popular technique in which basically you have like 5 or 10 or 100 different models and you generate predictions, and then you develop a system how you average those predictions or how you vote on those like use them as votes to actually generate your final prediction. And the more diverse they are, the better. And like that, it really gives you usually like 2 or 3%. Here I have an example, like if they're fully independent and each is 70% accurate, if you calculate their predictions by majority rule, and you're just predicting something simple like is it a cat or isn't it a cat? So like about 34% of the time, all 3 will be correct, and 44% 2 will be correct. And the accuracy will actually be 78% if you use simple voting among 3 models instead of just 1. So you get extra 8%. The reason why you got so much, because we assume that they're completely independent. Usually, as I said, in real tasks, you won't get that much, but you might get like 1% or 2 of improvement if you have a classifier, and like it might be enough to win a competition.
I'm sorry, before you go to the results, I have a question.
Yes.
So have anybody tried the denoising techniques? Like I just used yesterday in Audacity, and it was pretty good how the noise was, removed from audio. So I just Googled that. They use actually the Python package, and it's called noise reduction. So like any like non-machine learning techniques here?
It's possible that some people did that. I mean, mostly it was, I think some people did that, but I mean, like some people actually added noise because like for better training.
No, I mean, like, any kind of augmentation, because the one that you said about meetup, I mean, it makes sense, but the more augmentations you have, the better. So if you have like adding noise, removing noise, like doing this and that.
I know for sure that some winners added noise. I am not sure if, I think I might have seen someone mentioning removing some noise, but I would say adding noise was a more common thing.
Okay, let's put it this way. How big was the augmentation piece? Like from the results, do you think that was a huge piece of the winning solutions, or it was just a small boost?
I mean, I'm pretty sure it made the difference between winning and not winning, because like literally all of them used some augmentations. I mean, it's just basically the data set that was in that competition, it wasn't that large. So you kind of had to use augmentations to train a decent model there.
Yeah, absolutely. Okay, thank you. Thanks a lot.
All right. Yeah, any other questions? Well, I'll go forward. I guess we don't have that much time. So here is like a list of winners. It's interesting that both the first and second place were sole winners. They were not like teams of like 5 people or something. The third place team, Is This a Pigeon, was a group of 5 people. But I mean, I would say looking at this, the difference between first and second and third and third and fourth place was actually somewhat substantial by the standards of Kaggle competitions. Because like if you look, they're like, let's say between fourth and fifth and sixth and seventh, they're much more grouped together. But actually there was some pretty noticeable distinction in the scores of first, second, third, and fourth. Because like there are some competitions where it's like a difference of like 0.001 between first and second. So the first place solution, Ryan Wong, he used the sound event detection approach from the guy who took the 6th place. He's saying that he switched the CNN that was there to a pre-trained DenseNet 121. And like one thing that I couldn't understand from all of those notebooks of the winners is what they were pre-trained on. Because the GitHub repository for that paper where that sound event detection approach is described, it doesn't have any pre-trained models of this complexity, like DenseNet 121, for example. So there are basically 2 options here, and I'm not sure which one is correct. One option is that they just took DenseNet 121 that is pre-trained on ImageNet and used that. And another option would be that they actually went ahead and pre-trained that DenseNet 121 on that audio data set and then used that. And I'm not sure which one of those 2 is correct.
I think what they do is they take the pre-trained network that's pre-trained on ImageNet, and then they retrain it on the audio data. So they do start with the weights that you get using images. And actually that's really useful because you already have an algorithm that knows how to do things like find edges and dots.
Right. But the thing is, like, they have like for CNN, like they had that CNN 14, for example, that was specifically trained on that large audio data set. And then you can use it like it's pre-trained on the actual audio data, not the birds, but like those 632 or whatever is number of classes. So, I mean, I guess the third approach would be, to first pre-train, like take the one that is pre-trained on ImageNet, then fine-tune it on the audio data, and then further fine-tune it on this competition data. Yeah, I'm not sure. I mean, I didn't explore it to such great detail where I would find it. I don't know if this information is there or not. But I mean, in any case, yeah, it was pre-trained on something. And then this guy used no external data. Some people actually used external data because there is some other external data of birds, which was in some public repositories for this competition. And some people used that, but the first place actually didn't use that. But he used a lot of those augmentations from the audio augmentations library, like Gaussian noise, pink noise, Gaussian SNR, volume adjustment. Then he used cosine annealing with warm-up. I mean, basically the way it works is that you train, like it's the change in the learning rate. You first train your network that once you hit some local minimum, then you record the parameters there, and then you may switch the learning rate to be large to get out of that minimum, and then you train it again, and then you do it again. I have a slide at the end of the presentation that talks about that. And warm-up means that you first have a pretty small learning rate to make sure that it gets nearby some local minimum, that it doesn't just go away somewhere. And then you increase it, and then you do the normal learning rate schedule. And this guy used an ensemble of 13 models with and without mix-up by a specifically designed voting scheme. And my feeling is that like those voting schemes that people develop, like because it's actually pretty complicated here, like how do you do that problem? Like, let's say if you have 13 models and they all predict different birds for the same audio, then what do you do with all of that? So I think like a really well-designed voting scheme is something that was very important to winning this competition, actually. And like the first place, I think he actually talked about this being important. And yeah, I think this is like one of the reasons why he won, maybe.
I have a question, which is actually more appropriate to the leaderboard slide prior to this one. Cornell has an app that you can download onto your phone that does this. It'll do bird call identification. So you record a sound of a bird in the wild, and it'll supposedly tell you what it is. So they have something that they've deployed. Did you come across them saying how good their current solution is relative to this metric? Or,
No.
if they applied that to this data, what answer would they get? That would be really interesting.
No, I didn't see anything on that. I wasn't even aware of the fact that they had that app.
I've never gotten it to give me a very good answer on anything, but it exists.
Yeah, but I guess probably the reason why they had that competition is because they want to improve that app.
Yeah. I know Kiri made a comment that she didn't think these results were good enough for some kind of practical use. I don't know. I mean, all the ensembling makes it probably hard to deploy in a practical way, I suppose. But
yeah, but I mean, like, ensembling is basically just to separate, like to make sure that people can use whatever they want. But like, probably the models that won are actually better models as well. So even if you don't ensemble them, I don't think the people who won just because of ensembling, because everybody does that.
Right.
So
there's techniques for, you could take the ensemble model and do a distillation down to something more smaller, more manageable.
Right, but like, if you want to actually deploy it, then probably you can take one of those like winners models and actually just implement that. I don't know. I mean, like. Yeah, so like, second place solution, he also used the same sound event detection approach, but he used a bunch of different, like, the first guy, I think, just used DenseNet 121, he said. And this guy had an ensemble of 6 different, like, efficient nets, res nets, and dense nets. And he made a claim that he manually went through 20,000 training files and deleted large segments without the target bird. Which, I mean, that's a lot of dedication to manually go through 20,000 audio files and delete the silence in all of them. I wonder if this could have been done automatically, or, I mean, yeah, I don't know. And he used a lot of augmentations, like mix up, raise image to different power to accentuate either signal or noise, make it faster or slower, add noise. And also lowered upper frequencies, for which he suggested some scientific reason, because he said that higher frequencies in the wild, they either become stronger or weaker or something like that. I mean, if you follow that link there, you can discover, like, it's a scientific paper about actually, like, birds and frequencies and things like that. And as you can see, most of the winners, they actually have GitHub repositories with their solutions. So, like, anyone who is interested can go and check those out. Okay, so
sorry, I think I slandered Cornell a minute ago. I don't think they have an app for bird sounds. There are apps that will identify bird sounds. They have one for bird pictures. So maybe this is a new thing for them to go and to try to do.
I mean, I guess bird pictures is close enough.
If you usually can hear them and not see them, but sure.
Yeah, so third place solution, a team of 5 people, an ensemble of different ResNest and ResNext, which is a variant of ResNet with a more complicated block structure, essentially. And these guys actually used that additional external data that was available for training, as everybody used augmentations, adding noise, modified mixed up cropping, cross-validation. And also they used some sort of a custom ensembling formula, which they also mentioned, I think, that made a difference. So fourth place solution, kind of more of the same kind of thing, but these guys used efficient nets, B3, B4, B5, like medium-sized, pre-trained on noisy student. Again, I'm not sure if they did the pre-training themselves or just got those models pre-trained from somebody else, like from Google or whatever. And if you're interested in noisy student, I have a slide at the back that you can look at. Basically, you have one smaller teacher network that gets trained first, and then it makes predictions on some unlabeled data, and then all of that is, then a bigger student model is trained on all of that data. So it's like semi-supervised. And they also used a lot of augmentations here and cross-validation with multiple metrics. And then I skipped the 5th place solution. It's actually also, the notebook is available, but it was not very clear to me, like it was more of like an exploratory kind of thing that where they didn't say very clearly like the sequence of steps that they did. But the 6th place solution, I thought I would mention it because that was the guy who actually created that notebook that everyone used. And basically, he used like 3 stages of training to gradually remove noise in labels, not the audio noise, but basically he referred to weak labels, as I said, like you don't know where the bird is, referred to that as part of the noise, but also he said that some of the birds might have been missing there. So basically he used some sort of a 3-stage retraining system where he would train the model, then predict on the same data, and maybe discover like the specific intervals using the sound event detection, like in which specific segment of the audio that bird was, and then he would train a new model on that. And he used a bunch of other techniques, like again, augmentations, cosine annealing, stochastic weight averaging, which is another technique that I think I have a slide for. So instead of just using the weights of the latest model, when you train the neural network, you take the average of the weights of the last iterations, last epochs that were trained, and you like calculate either an exponential moving average or some other kind of average. So that's another method that people use there. Yeah, so basically the conclusions, all of the best results were achieved by standard 2-dimensional convolutional networks like ResNets, DenseNets, efficient nets with that sound event detection framework. And again, I'm not sure like exactly what they were pre-trained on. And augmentations are definitely essential because it's a small data set. And ensembling, I don't think it's also essential in terms of winning the Kaggle competition, but it's pretty straightforward for everyone to do. So I don't think it made a big difference in determining the order of the leaders because everyone did it. And I mean, basically the lessons, like if you want to win, like pretty much everyone just copied that notebook of that guy. Like in general, like my experience with Kaggle competitions is that like never to try to code everything from scratch. So like borrow from all of the notebooks that are available. It's because otherwise you'll just run out of time. And yeah, like this guy only finished 6th. Maybe he would have finished 1st if he didn't share with anyone. So I mean, definitely if your goal is just winning, then you don't want to share your good ideas there. So I guess this is the end of my presentation. If you guys have any questions, I'd be happy to answer them.
One question about the structure of the competition. So the data set, were you able to download that and then do some training on a local machine? Or did it have to get loaded in a notebook and not available?
Yes, the training data, you could download it on your machine and like, do all kinds of training, yes. But the test data was not available.
Right.
And that created a big problem for a lot of participants or all of the participants because, I mean, there was one sample of like either one or two files, I don't remember, of test data of what the test data looks like that was provided to the participants. So, and it looked quite different from all of the training data in the way that, as I said, it was much longer and contained multiple birds. So.
Yeah, I did one kernel competition, and the only way to get the data was to load it in real time in the notebook, and you couldn't download it.
But there must have been some sort of data. You mean like you just had to do everything in the notebook?
Yeah, you couldn't do anything offline. But it sounds like this competition is set up differently, which is
no, this
better.
competition is set up differently. I mean, like you can go right now and like download the training data and look at it if you want. You can download the test data, but
cool.
So something that I tried to figure out, and I think because I wasn't in the weeds of the competition, I couldn't get to, but I think is a very interesting question. So if you look at the leaderboard and you study the up and down, actually you need more rows than you have on your slide. So I'm looking at the top 50 on the leaderboard, and I'm looking at the shakeup, right? So this is the difference between how people performed during the competition on the public test set, and then how people performed on the final test set. And so 3 observations. One is that, there's a bunch of like little bit of movement, right? Like the person who won moved up 6. There's like a +1, -1, things like that. There are a couple of people in the top 50 who moved up a lot. So, for example, the person who finished 21st moved up 339 spots. That's quite a lot. The person who finished 42nd moved up 716, and then the person above them 856. So that's a lot, which is interesting. But actually, the most interesting data point on this leaderboard is the person who finished 39th, because that person was first on the public leaderboard. They moved down 38 spots to 39, and they are the only person who moved down a lot out of this top group. And they had a write-up, 39th place solution first on the public. And I cannot deduce why I think that happened. Like, there's no way that's a coincidence. This is not a draw from a random distribution, like, that gave us this result. And
well, I mean, my guess would be that this person used some kind of trick that just happened to work really well on the public leaderboard, but was specifically like overfitted to that public leaderboard somehow.
Yeah, you often find people overfitting to the public leaderboard, and that usually results in a plummet when the final tally is done.
Actually, I would expect that to happen to the second place, because he was like cutting the noises and stuff, like, removing like different parts of the video. So that would be a reason, but it didn't happen to him.
Well, I mean, like just the fact that they cut the noise or stuff like that. Like if you're careful not to overfit, then I guess you can do it. Like
I'm talking about the guy who went and manually, like, removed like all parts of the audio that were not relevant to the birds.
Yeah, but like, why do you think that this would?
But this is something that would be different from all other people. That's what I'm saying, is that nobody else did that. So
yeah, but maybe that actually helps. I'm not sure what this guy's position was on the public leaderboard. But because, I mean, once you train a model to actually recognize a particular bird, the fact that you have periods of silence there shouldn't really make your model like perform worse.
It's not a silence. That's what we talked about. So it's not like, because the background can be anything, right? And that's why I'm saying removing a background removing those parts where there is no birds would actually affect.
But you would presumably still have that background in the parts that had the bird in it.
Well, anyway, I just said that according to that, Alexei, like what he could do to go that way down, I'm saying that's something like that would probably, but I cannot think of anything else.
Yeah, I don't know.
In the 5th place solution, the guy writing said that he had used the leaderboard, the public leaderboard, to tune his guess for what fraction of the data should be no call. So you can have one of like 250 type birds, and then one of the options is also there's no bird. And so if your training data has a different ratio of no call, and in the training data every signal has got a bird in it, so you have to kind of guess at how much you should be guessing a no call going from your training data to the test data. So some people, the first place guy that dropped to 39th, he might have just made an unlucky guess at for the value of no call.
Maybe, yeah. I mean, like basically, yeah, he did something that happened to work well on the public leaderboard, but not private. And I mean, like, unless it's somehow mentioned in their notebook, I don't think we'll ever know. I mean,
well, I mean, so I looked at his discussion, and he definitely, like, so this 39th place writer definitely was paying some close attention to the data. There's some very specific discussion about frequencies and sampling rates and so on. So, and it may be worth just touching on this topic is that this competition, like as you sort of touched on a little earlier, is an example of a kind of, there's a domain transfer we're trying to achieve here, right?
Right.
We have, like, we know for sure the test data is a bit different from the training data. And so getting over that hump is definitely difficult. And conceivably, in fact, the two test data had something systematic. Like this may not just be like badly behaved, like I made 100 submissions and I picked the highest one, but that doesn't generalize to unseen data. It may not be that. This may be actually like something was systematically different about the public test data than the private.
Right. Yeah. I don't think it was just one like particular pick that this guy did. I think it was something in his method, like maybe he had like 100 or whatever solutions, but they all had some sort of like a systematic assumption that was just not true for the test data.
Yeah, and I think it's actually I think it's unfair to run a competition like that. I think any practitioner has knowledge of their target domain. Like even if they don't have data from the target domain, like, and you could construct real life examples where you would at least know what to expect based on, I mean, domain knowledge.
Well, I mean, I don't know if I would agree that like any practitioner, if you're trying to develop a model for some kind of future predictions, you might not really know what, like things can change with time. So I think there is some practical usefulness to actually this kind of transfer.
Yeah, fair enough.
Maybe also worth noting that a lot of people said they use the public leaderboard as their validation set.
Right. Yeah, and I mean, like when you have this kind of like when you have like a different test data from the training data, you kind of have to decide what to do. I mean, I remember like when we participated in the data science bowl about 2 years ago, it was a little bit like that as well. We were predicting, like it was like a visual competition, like predicting cell nuclei in medical images, and the test data was actually quite different from the training data, and we kind of had to make a call, like which model do we want to use. And I think we actually had an option of submitting two there, so we kind of chose the two that because there were two people on our team, so and we were allowed to submit one per person, I think. Yeah, but yeah, it's a hard question. Like, yeah, like if you know that test data is different from the training data, but you don't know how, then yeah, like what do you do? It's basically
and I agree that there's like how to say there's probably a best thing to do, you know, like you know, when faced with an unknown distribution, you can sort of maximize your expected performance or minimize your worst case or something like that. But I do feel like in a competition environment, it becomes a bit more like a lottery where, like, you know, doing the sort of average best case thing isn't how you win. How you win is you take risks, and then if 100 people take risks, somebody gets to be the one with the
right. Yeah, probably that's true. Like if it depends on your goal. If your goal is to just like win a silver medal or something, then you might actually opt for the save option if you think you have them. Like if you know that you're finishing somewhere between like place 30 and place 100 and you don't really care where, but you just don't want to take a chance, then you might actually choose the safe alternative. But if you're somewhere near the top, then I guess it makes sense to take some chances. Yeah.
Was there any entry who used just a straight up waveform model without using like a 2D image?
No, I mean, I'm pretty sure there must, like, out of 1,390 people, there must have been some entries like that. But I mean, none of the winners did that.
So what I remember, the pen is kind of like they use like a waveform. They, in addition, as well as working on the spectrogram, they also use just
okay.
Convolution.
If you mean that, yeah, I think actually some people did mention using that as some part of. I think they mentioned that it didn't either didn't work well or didn't provide particular benefit in this case. But I might be wrong because I mean I looked at that paper, but I didn't like try to understand precisely how it worked. So I mean I remember it mentioning this waveform model, and yeah, like in the paper they're saying it's actually a little bit better than like the standard like log-mel spectrogram. But I think some of the winners mentioned that it didn't particularly help, but I'm not 100% sure. I would have to look it up.
So go ahead.
Go ahead.
I was going to ask, did anybody comment on what time or frequency resolutions seem to be important, or how do they select the time and frequency resolution? I didn't see anybody.
I don't think it was like a major thing, but I'm pretty sure some people mentioned what they like. A lot of people mentioned what they used. I'm not sure if anyone specifically discussed like. I think most people, they just said, okay, I used like 512 or whatever. I don't think most people actually provided any reasoning as to like why they chose their numbers. I mean, at least I don't remember seeing that, but some people might have.
I maybe want to add that using the spectrograms is actually sort of intuitive, because if you think of your brain and your ear, when you're hearing something of a certain pitch, you have a whole bunch of little hairs in your ear that vibrate at a particular pitch. So what's coming into your brain is already Fourier transformed. It's already a spectrogram. So whatever your brain is doing is probably doing the same thing on visual information as it is on audio information, because the audio information is already a spectrum.
Right, but it's not just the perception, it's the actual like bird, like different birds, like basically the main frequency of each bird, I guess, is determined by the specific size and shape of their like inner like throat. So if you have a larger bird, they'll probably have lower frequencies. If you have like a smaller bird, I mean, it's not 100% guaranteed, but in general, like the frequency might actually be quite specific to each type of the bird.
I don't know. I think actually that because birds don't only have to listen to other bird calls from their own species. They have to listen to crunching in the underbrush. And if they're going after prey, they have to be able to hear the prey. If they're trying to avoid being eaten, they have to be able to hear like footsteps and stuff like that. So my hypothesis would be that birds, the audio range of frequencies that birds hear well in is probably pretty close to the range that humans hear it.
Yeah, but what I mean is I'm not talking about the range that they can hear well. I'm talking about the range that they can actually produce. Like we don't know what birds think, but like in terms of humans, you can hear a wide range of frequencies that you can't really produce. So I mean like if you hear you can hear some really low frequencies which you would never be able to produce with your voice. So like the fact that they can hear a wide range of frequencies doesn't mean that they can actually sing on a wide range of frequencies.
Well, when you identify the bird, like a bird or like an insect sound, it has they have like a repeating pattern. So I think in if we just look at identifying the bird sound, I think looking at the frequency domain is quite useful and natural. But it's a sound event detection. So when you want to detect when certain sound occur in time, then it's kind of nice to work on time domain directly without going to frequency domain. I'm mentioning because starting last year, I saw a lot of interesting papers on the why not just use 1D convolution and just work on straight from the time domain.
Yeah, I mean, I'm absolutely I'm not an expert on audio data, but I'm absolutely sure that it's possible. I mean, the information is there, whether you convert it into the frequency domain or not. The information, you might actually lose some information when you do the conversion. But so in theory, you have more information without the conversion into the frequency domain. So if you figure out exactly how to train the right kind of an algorithm, the right kind of neural network or whatever it is that you're using, it's just a lot easier since you can just use convolutional networks in the frequency domain. It's just a lot easier to come up with the specific way to train that model, the way I see it. But yeah, I mean, you're absolutely right in the way that it should be possible to train a model just in the audio domain. And I mean, I don't remember the details, perhaps what they did in the last part of the paper is maybe they just did it in the time domain. Yeah, I don't remember exactly.
I think I agree that you could end up with a model just by without doing the spectrogram and by learning with 1D convolution filters. But the thing is that this data set is pretty small. So if you have to basically relearn how do I make a spectrogram, then you have a whole bunch of free parameters that you have to use to learn how to do the spectrogram, and you can reduce the sort of parameter space that you have to search through by having the spectrogram that you already know how the formula about how to compute it, and that saves you having a bunch of free parameters and potentially stops you from overfitting.
Right. So yeah, a lot of people, they use pre-trained models. So yeah.
Sorry, Stan, I'm going to jump in here because I think that we probably set the record for most number of post questions to a talk, Stan, so great job with that. Very interesting discussion that you've led so far. I just want to kind of call an official close to the meetup here because we've got a lot of people dropping off, and I think a lot of people want to have a chance to say thank you, Stan, and to give join me in a big round of applause for Stan. So on the count of 4, I'll count down. 4, 3, 2, 1.
Thank you, guys.
Yeah, really great.